Alright, welcome back to another AQA A-level chemistry video. And yes, I know, I've been out for way too long and I didn't really keep it to my word. I said I was going to finish off all the videos before the start of I was going to finish off all the content before the start of the exam. And now, by the time you're watching this, it's way past the end of the exam now. And the idea now is that I mean, if you're watching this now, for someone that's, as a usual subscriber, it's probably is completely useless to you because you probably have already finished your exam now. So you wouldn't have selected this video anyway. But to stop the waffling, what I'm going to be doing now is I'm going to finish off the rest of the content. Hopefully by the end of the summer holiday, I'm going to be preparing these videos for the next cycle of year 13s so that all the content is done. You can watch the previous videos because it's all the same. The content, I don't believe there's going to be a major difference in the content that you're going to be revising. But in terms of that, I'm going to try and finish off the rest of the content. It's all now on Inorganic Year 2. I've already done one part of Inorganic Year 2. And that was to do with the period 3. But I'm going to make sure to do transition metals and reactions of ions in aqueous solution, those type of topics afterwards. But yeah, so this video is going to be on substitution reactions, and I believe the last video that I done, even though it was really long time ago, I talked about the general properties. Now, looking back at it now, that video, although it was very basic, it is pretty much a glossary, really, into what we're going to be going on to next. So in that video, it was on general properties of transition metals. I talked about the fact that transition metals are metals and that they have properties of metals that you'd expect. So the fact that they are hard, shiny, sonorous, good electrical and thermal conductors, that type of thing, because they are metals. But specifically, transition metals have properties that are very unique for transition metals. So they have multiple, for example, they have multiple oxidation states. And there's other things that link into the fact that they have multiple oxidation states. They form colored ions. They can undergo. They can act as catalysts because of the fact that they have multiple oxidation states. There's also another thing as well, is they can undergo reactions with ligands. Now, this video is going to be talking a lot. I remember I mentioned what a ligand is from that video, but in this video I'm actually going to explain what type of reactions that they would be doing with ligands and generally what type of reactions that you'd expect from substitute. You can already tell from the title it's a substitution reaction, but it's not as simple as just saying substitution reactions. There's multiple types of incomplete and complete substitution reactions, and I'm going to be going through that in the video, and it all depends on the type of ligand that you have, as well as really the oxidation states of some of these compounds. But I'm not going to overcomplicate it, right? The point being that the last video, everything that I talked about is going to be, or at least for ligands, it's going to be in this video. But for talking about multiple oxidation states, there's going to be a video on multiple oxidation states and things that are related to that, the colors of the ions, titration, catalyst, both types of catalysts that they expect, and so on, right? But let's get straight into the video. And I've wasted a lot of time just doing a little intro there. It's been a very, very long time for me, so forgive me. I would have probably left a timestamp to help out with that little thing there, skipping all that waffle out. But anyway, without further ado, the ligands of complex ions can be exchanged for other ligands. So this is called a substitution reaction. So the common ligands that you'd expect, most common ligands that you'd see in your exam, or for when you see, we call them complex ions. Yeah, so a complex ion is just the transition metal ion that's surrounded by the ligands. Did I mention it? Yeah, I already mentioned in the previous video, so I don't have to go into too much depth of what a complex ion is. But the most common ligands you'd expect to see in a complex ion are water, ammonia, and chloride ions. So you expect I'm going to go into chloride ions a bit later, but ammonia and water are of similar size and have no charge, whereas chloride ions are large and have a negative charge, and that plays a massive influence as to how many bonds you're going to form or how many, we call them coordination numbers. Did I mention what coordination? I think I did mention what coordination numbers are in the previous video. If you don't know what they are, if I forget, I'm gonna leave a link in the description. If I forget, comment, let me know, and I'll make sure to do that. But it would have been the previous video anyway. But because of the relative size and the charge of a ligand determines the coordination number, i.e. how many of that ligand is going to bond with the complex ion, or how many bonds are going to form the complex ion. Now chloride is just going to be one, it's only forming one bond anyway, so it's only going to have it's only going to form one bond. But because it's so big, you can't fit that many chloride ions actually around your transition metal, whereas you can do so with ammonia and water. And I'll go into that in more detail a bit later on, right? But substitution reaction, so ligands can be exchanged. So a good example is the interconversion of copper hexaaqua with a 2+ charge and copper ammonia. Copper 2, I'll call it copper 2 ammonia. Copper hexaaqua 2+. I mean, if it's a hexaaqua, I don't really have to mention the charge. You can see the charge there already, right? But substitution can be, so a good example is interconversion of copper hexaaqua and copper hexaamine. Substitution can be also incomplete. Sorry, let me go back on here. And I didn't really explain what I meant on here. So with this one here, if I explain this one a little bit better, because I didn't explain it very well. So a good example is, so ligands can be exchanged, right? So if I was going from copper hexaaqua I can convert copper hexaaqua into copper hexaamine. Oh. By a substitution reaction. The actual substitution that's actually going on in this case is that we're adding 6 moles of ammonia. And this would be, and if they ever talk about the conditions, I'm pretty sure they do talk about the conditions, it would have to be with, it will be in excess. If you want to get the complete reaction completely, it would have to be in excess of ammonia. I'm pretty sure it's going to be ammonium bromide, if I'm not mistaken. But I'm not going to be talking about if I don't mention in here, then I probably won't talk about the conditions. But the conditions are very important, and you probably get that type of information either from your teacher or from doing a past paper, because this type of question comes up quite a lot. But substitutions can also be incomplete. Again, whether it's complete or incomplete is completely dependent on the conditions of the reaction. I assume if it's incomplete, it will be in a dilute solution of, in this case, if we're going from copper hexaamine to Cu or copper NH3 H2O2, it's probably because it's an incomplete or very low concentration of water or very low volume of water. Again, I'm not going to go too much into the conditions because I've forgotten them. It's been a very long time since I've done this type of content. But I will remember that it's definitely to do with the conditions. And you can get incomplete as well as complete substitution reactions. Now, the coordination number. The coordination number can change in a ligand substitution reaction. And this usually happens when substituting ligands of a different size. So if I'm going from cobalt, in this case, cobalt hexaaqua, and I expose it to 4 chloride ions, so from 4 HCl, you're probably exposing it to a solution of hydrochloric acid, of which the hydrochloric acid will dissociate and you get the chloride ions. There will be a change in not only just the coordination number, but also there'll be a change in the charge. So it's best if I get, so if you can imagine cobalt, let me actually know what I'm gonna go and let's get a sketch, right? So we have cobalt hexaaqua, right? As this is going to be a bit long and kind of awkward. 4, 5, 6, 7. Right, cool. And all of this, because water hasn't got a charge, so cobalt is actually a 2+ charge, right? And because water doesn't have a charge, it just means that the whole thing has an overall charge of 2+. But if I expose it to 4 chloride ions, you got to remember that chloride ion, in comparison to the water, is kind of like this, right? This is probably not the best way I could show it, but and then water's like, if you're comparing size, it's kind of. Now I'm gonna don't get hooked up on that being to scale, because that's obviously probably not to scale. But the idea being that chloride is a much bigger ion and it's also charged. So, and I probably should have put the actual charge here, and that affects the shape of our. It affects the coordination number, and if you're affecting your coordination number, you're going to affect the shape of your ion, of which you will also need to know. As part of your exam, you need to know the shapes of your molecules, which is something that you would have learned from. You would have learned that from what? Physical chemistry. But yeah, it's there's a couple names you probably have to know. But is there any extra? Probably like. No, it's not extra names, but you just need to recognize the shapes of these molecules. But the idea being, if you're affecting the coordination number, if you change the ligand, you'll change the number of coordination number. You change the coordination number. If you change the coordination number, you change the shape of your molecule, and ultimately, this is something that you will need to understand. Without me waffling on too much, we're changing coordination, and it also changing coordination number will then change the number of moles you have in your products and in your reactants. So we're going from here, a coordination number of 6. Well, actually, I'll just show you. 4 Cls minuses goes to form cobalt tetrachloride. We can only form 4 here. So cobalt tetrachloride. Now, it should be made obvious that these are dative covalent bonds, right? So the bonding pair is actually much closer to the oxygen than it is actually towards the transition metal. But let's just do that. This is actually more of a. Haven't got too much time to go do the 3D models of all of them, but now that I've done that, this is also an ion. And you have to also, if you ever told you to write this down, you have to show that this is first of all an ion. Hopefully you have more space. I'm going to write it up here because there's not much space here. But if we've changed the coordination number, so we've gone from +6 here to a coordination of +4, but we've also changed the charge. Because remember, this here was, we said it has an overall charge of 2+ because it has, cobalt is an ion of 2+, but at the same, also water doesn't have any charge, so we just said it had a 2+2 charge. But chloride ions have a -1 charge, and we've added 4 of them, so we're just going from 2 minus 4 equals -2. This is a negative. The overall charge of this ion is -2 or -2. I never say -2, -2. But things like that can change. If you're going from cobalt hexaaqua to cobalt hexaamine, it's pretty much no change, because all you're changing is the ligand, but there won't be any drastic change because ammonia and water are of similar size and charge. Whereas going from cobalt hexaaqua to cobalt chloride, there'll be a massive change. There's a change in the coordination number, shape, and charge. So coordination number. And if they ever ask you to write a longer type question or anything like that regarding, because they may ask you a longer styled question regarding complex ions. The main things when you're talking about complex ion are the coordination number, the shape, and the charge. And if there's anything else, you'll be screaming at me at the screen. Maybe not. Maybe we'll just be looking at the screen thinking to myself, why the fuck is this guy still speaking to me? Probably. But where was I? Yeah, so the coordination number can change, and I think I've already said that. Yeah, so the coordination number doesn't change when substituting water for ammonia because they're of similar size. All right, so that's everything I've said right now is very basic level of substitution reactions. Now we have to get back into slightly. There's one big thing when it comes to substitution reactions that this tends to be a 6-mark question in the exam, and it's something called the chelate effect. And it's actually really easy to score these marks in the exam if you understand entropy. It has a major link to entropy, and I'll go through it later in the video or in a couple of minutes in the video. But the chelate effect is something that usually comes up a lot in this topic, and it's like the easy 6 marks if you know how to answer it. It may be slightly more marks, but I'm going to go straight into it. So some ligands can form multiple dative bonds with transition metal ions, and this leads to some important chemical reactions. So the chelate effect will go on to a bit later, but it's also something that I touched on it. I just spoke about here in terms of the number of dative bonds that you can have. So the number of, I said here that chlorine, water, ammonia, they all form one singular dative bond. If I go back down here, they all form one bond between the ligand and the transition metal ion, one single dative bond, right? Whereas there's some ligands that can actually form, because of its shape and its structure, they actually form two bonds, two coordinate bonds, dative bonds, coordinate bonds, call them whatever you want to call them. They can actually form two bonds with the same transition metal ion. However, in some of those cases, they don't actually change the coordination number. So it may be the fact that, and I'll go through what some of these ligands are called and what they look like, but remember what we know that the coordination number, the only thing you need to know about coordination number, the coordination number is just the number of dative bonds between the ligand and transition metal ion. So here we have 1, 2, 3, 4, 5, 6. So the coordination number here is 6. Don't lose track of that because I'm going to go on, because it's something that some people usually get confused upon, and I'll explain that soon. But I'll go on here and say that denticity. So denticity describes the number of dative bonds that can be formed with a transition metal by one ligand. So a ligand that can form 2 bonds is called bidentate. A ligand that can form 1 bond is called monodentate, and a ligand that can form multiple bonds is called multidentate. So the ones that we cover right now are called monodentate. So a ligand that can form 1 bond is called monodentate. So water, ammonia, chloride ions, they're all monodentate ligands because they can only form one singular dative bond between the transition metal ion and the ligand itself, only one, right? But there are examples of multidentate and bidentate ligands. There's more than, I'm going to show you a couple of them here. There's much more, but I'll show you a couple of them down here. So I'm going to first will show you some of them, and I want you to actually, you know what, I actually want you to name some of these as well. So I'll give you a couple seconds, just pause the video now and try and name some of these. So I've paused the video here. So I assume you've paused the video, or maybe you haven't, you just looked at me like a waste man. Fair enough if you have. But we know that this is ethyl ethyl 1,2-diamine. So the first thing I wanted you to name them, but I also want you to see where the binding sites of these ligands could potentially be. So I should have probably said that earlier. So I wanted you to name them, but I also wanted you to label the binding sites, so you can draw a ring around them, whatever you want to do. If you're doing, why would you draw a ring around them? You can't even draw a ring around them. I don't know what I'm talking about. But yeah, I just wanted you to be able to see, or in your head think, where would the potential binding sites of these ligands be between the ligand and the transition metal? Where would the dative bond be, right? So with ethyl 1,2-diamine, and I guess I've already technically done this one with that was ethane dioate, or otherwise known as oxaloate. Right, I don't know why I left this one here, but that's just basically the same thing. Now, I'm going to draw a ring around it, and hopefully you can see how ethyl 1,2-diamine actually forms around a complex, or forms a dative bond around a complex ion. So it has one here. It's actually with the nitrogen. The lone pair on the nitrogen is responsible for actually forming the dative bond with the, and that's very important. Actually, I should have. That's why I drew out the structures of ammonia and of water, because some people actually, in the exam, there are instances where they ask, it's a 1-mark question, or maybe it's sometimes a 2-mark question, where they ask you to draw a ring around the atom that forms the bond, or the atom that's responsible for forming the bond with another compound. And the common mistake that people make is that they don't read the question properly, and they draw the entire, they'll, if they tell you to draw a ring around it, they'll draw a ring around the entire what's it called, group, and it's not the group that forms the bond. In this case here, it's the nitrogen on the group. It's the nitrogen on the amine that has the extra lone pair that's responsible for forming the dative bond between itself and the transition metal ion here. This isn't involved, this is not involved, that's not involved. It's just the lone pair on the nitrogen. So it's here, here, and I think you can already see where it would be on the oxaloate. But there's one here, here. Did I say draw a ring around it? Did I say, no, I just said label. That's good. And I've pretty much already done it here, but I've done oxaloate here and ethyl 1,2-diamine. Now those, so oxaloate and ethyl 1,2-diamine are called bidentate because they form 2 dative bonds between the same transition metal ion. So both of these will bond to the same transition metal ion, right, on the same compound, right? That's what they're called bidentate too. EDTA is an example of a multidentate ligand. In this case, it's 4, but anything more than the 2, we just say multidentate ligand. Now, EDTA is a big old, it's a big old ligand, and I forgot what it's actually used for. It probably has, I know it has a big use, but I've forgotten it. Again, I apologize for not doing these videos more consistently, but it is what it is. But I think you can already see why it's EDTA 4-. Try to make it as clear as possible. It's because of the negative charges on the oxygens here of this carboxylate group, and these are going to be the binding sites. So all of these can form, all of these binding sites on these oxygens from the carboxylate are going to be the binding sites for the dative bond on the transition metal ions. So all of these oxygens, these ions here, are going to form one dative bond each on the same transition metal ion. I know this one might be hard to believe, but it actually forms a very, there's an image on Google that's probably a bit better at showing it, but they're all, if I was to show it here, it's actually really interesting where it actually undergoes a conformational change in shape, where the ion will, say the transition metal was, say, copper, right, with 2+ charge, the whole structure of EDTA will change its shape to accommodate. So it's like kind of like a I don't know if you've ever watched Spider-Man, when he's like, multiple webs, he's holding multiple webs at the same time, he's kind of pulling something together. I should have used that example from before. Let's just go for this. I know it's like a terrible drawing of Spider-Man, right? But he's kind of like in the center, and he's like holding all of them together, like holding everything, like maybe a building apart here and a building apart here, and he's like kind of like holding it all together, and he's in the center. That's what the transition metal is like. It's going to be in the middle, and it's pulling everything inwards, and that's what it would look like. That's what it looks like here. So all of these binding sites are bonding to the same transition metal ion, but in this case the coordination number would just be 4, right? The coordination number would just be 4. 1, 2, 3, 4, and it's actually, the bond is so strong that it's actually pulling the structure of EDTA to kind of like inwards, pulling it in, right? But the coordination number is 4, but the number of ligands is 1. There's only one ligand here, right? The coordination number is just the number of bonds between the transition metal and the binding sites of a ligand, really. That's all it is. So the chelate effects. I said I was going to mention the chelate effect and what it was. So the chelate, so multidentate ligands will almost always replace monodentate ligands at a metal center, and this is called the chelate effect. Now the chelate effect is largely an entropic effect. So when you substitute a multidentate ligand for a monodentate ligand, you increase the number of moles of molecules in the products of the reaction, and this leads to a large increase in entropy, and this brings the Gibbs free energy below 0 for the change. Now if you read all of that and you said to yourself, what the fuck is going on here? What's he talking about? It's very complicated. I don't know what he's saying. I'll show it to you here, right? So I'm going to show you example of let's just bring this down, right? Right. So I said that if I was going for, let's say we're going to do a ligand substitution reaction between let's just say copper, I don't know why I keep changing that. I wanted that. Copper hexaaqua, right? Copper hexaaqua. Why did I do that? Copper hexaaqua and EDTA. I'm going to explain to you why this reaction is going to be more favorable than the other way, or why higher rated ligands, I'm calling them ratings because I don't know the other way of explaining, but if it's a multidentate, or if it forms more bonds or forms more coordination numbers, if you're forming a complex ion with a higher number of with a ligand that's for example, if we're going from monodentate to a bidentate, that is more favorable than going from a bidentate to a monodentate. And the reason for that is as simple as saying this, right? So if let's say we're going to go from a monodentate ligand complex ion, which is copper hexaaqua, and we add EDTA, so we're trying to form copper EDTA, right? EDTA 4 minus, right? We know that the products of this reaction are going to be, in this case, it would be copper EDTA 2 minus plus 6 moles of water. Now, what the chelate effect is saying here, right? The reason why this reaction is more favorable is because look at what's actually happened in this reaction. Look at the change. It's an entropic effect. Remember what we did in entropy? We talked about entropy is a measure of disorder, right? And when we're talking about entropy, we're talking about the Gibbs free energy equation, right? I'm going to write the Gibbs free energy equation here. Delta G is equal to delta H minus T delta S. Now remember what Gibbs free energy is. Gibbs free energy is just a measure of telling you how likely or how feasible a reaction is. And we said that the more negative the Gibbs free energy is, the more feasible, i.e. the more likely the reaction is to occur. And we determine that by this. This is essentially determining what our Gibbs free energy is going to be. If minus T delta S is greater than delta H, our reaction is going to be favorable. Now, the temperature isn't going to be something that's going to be affected in this reaction, right? Because we can maintain the same temperature in this reaction. But what we can alter in this case is delta S. Now, I said this is an entropic effect because remember, we're going from entropy is a measure of disorder. And if we look, we're going from, there's a number of things that can affect disorder. I believe pressure, temperature, and the number of molecules, the concentration. Now, if we go from here, we're going from 2 moles, 1 and 2. There's only 2 moles of copper hexa aqua and 1 mole of EDTA 4 minus. 2 moles, 2, 6, 1, 7 moles. There's a 2 to 7 molar ratio. We've increased our molar ratio by 5, right? So we've increased the number of moles in our products. We have more moles of product than our reactant. Therefore, the reaction is going to be more disordered, or increasing disorder, or less ordered, right? And therefore going to increase therefore entropy increases. So if we're talking about, if we're going down and put, this is the 6 marker essentially. This could be potentially a 6 marker. Why? They'll say, why is this? They could ask questions saying, why is a reaction between a monodentate to form for example, they might say, why is it more favorable for copper hexa aqua to form EDTA 4 minus? And the first mark will be talking about the fact that you'll be mentioning the type of ligands that you have. So saying you have water is a monodentate ligand and EDTA 4 minus is a multidentate ligand. The second mark would be for writing out an equation. The third mark is for then mentioning and realizing that there's a 2 to 7 molar ratio. And what does that mean? It means that we have increasing number of moles in our products compared to our reactants, right? So one is saying types of ligands. 2 is mentioning, I was going to write it down, right? 2 is writing equation. Now, this may not be the exact way of the mark scheme, and always follow the mark scheme, but the way I see it when you're breaking down this question is talking about the types of ligands, writing the equation, the third part being recognizing increase in moles. And when you're recognizing the increase in moles, you're recognizing a change in entropy. And then the fifth would be realizing what does changing entropy actually mean, and I'll say that where it is. So so what does that affect? And then your conclusion is mentioning the Gibbs free energy. So I'm going to go into detail. So I'm going to go back into detail. So the first one I said was type of ligand, and then you'll write out your equation. So mentioned, so first of all, saying that in this case, water is a monodentate ligand and is a very small ligand that forms one singular bond between itself and the transition metal ion, whereas EDTA is a multidentate ligand that forms multiple coordinate bonds between itself and the transition metal ion, and then you write out the equation. Writing out the equation just helps you set up the rest of the answer, right? The third part will be recognizing that there's an increase. Once you've done it, the equation, and it's balanced, you'll recognize that there's an increase in the number of moles, which means that there is going to be more disorder. There's going to be an increase in disorder, and therefore entropy increases. So if there's, you recognize that there's a change in entropy, and recognizing that there's a change in entropy doesn't give you all the marks. You have to say, why is it important? What's the relevance of the change in entropy? And the fact that saying that if entropy increases enough, T delta S, and this is the key part, is greater than delta H. And if that's the case, if T delta S is greater than delta H, therefore it means that your delta G is going to be negative. You're going to have a negative, because if this value is greater than this value, delta G will be less than 0. And if delta G is less than 0, your reaction is going to be feasible. And that's it. That's your marks. Now, counter to this, what if it was the other way around? Why is the other flip side of the reaction going to be less feasible? Let's say that this was a reversible reaction, which I guess it really isn't, but say I was to do this the other way around. Why is it be less feasible? And it's just recognizing entropy. It's just simply recognizing entropy. We're decreasing the number of moles in our products. Therefore, the reaction becomes more ordered. Entropy decreases. T delta S is less than delta H. Therefore, delta G is more than 0, or is less likely to be less than 0, or just saying it's less than 0. Sorry, it's most likely to be less than 0. So it's delta G is more than 0. Our reaction, delta G is positive. Therefore, if delta G is positive, our reaction is not feasible. And that's just all it is that you're recognizing there. I know that's a bit long-winded, but I just wanted to make that point very clear, because it actually helps for the rest of the answer. It helps for understanding what the chelate effect is by actually writing and drawing it out. But yeah, so another example, a great example, that's the main part that you need to know. And in terms of the rest here, this is something that you should know for your exam as an example. You don't need to know too much in depth of it, but the heme protein with heme prosthetic group on hemoglobin, the heme protein is found in red blood cells, and that is a complex ion. It's a complex ion. You already know it has iron in it, and you probably have recognized this structure before. But it is just a massive complex ion, and it works in the same way. So it has an iron 2 ion in the center of the multidentate ligand. So again, these are, it's a this is a ligand. This whole thing that's surrounding the ion is the multidentate ligand. I think it's called a porphyrin group. But I'm not going to go into too much detail. You don't need to know about that. But all you need to know is that in the lungs, oxygen binds to the iron 2 as a ligand. So what's occurring here? Oxygen is binding to the iron as a ligand. It's a ligand substitution reaction in essence, right? So in the lungs, oxygen binds to the heme protein as a ligand, and then can be transported around the body by the protein. In the body, the oxygen concentration is lower than in the lungs, And if you did biology, you know that this is to do with the partial pressures, but I'm not going to go talk too much about partial pressures. But in the body, the oxygen concentration or partial pressure is in the body is lower than in comparison to the lungs. So the dissociation of oxygen is favored. That's all that happens. So once the hemoglobin's gone to a part of the body that has a low concentration of oxygen or partial pressure of oxygen, the oxygen then gets associated to that part of the body, and it comes back to the lungs where oxygen concentration is higher, and that the oxygen associates or binds to the iron. But again, you don't need to know too much detail about this because it is in biology, but you just need to just have an understanding, knowing that this is the more important part you need to know, and this part here is the more important part that you need to know. But just having an example, because they may throw it in the exam saying, oh, what's going on here? Just knowing that it's just a ligand substitution here where oxygen is just binding to the group, or it's just binding to the iron here, and this is just this is just a multidentate ligand in a complex iron, right? Now, carbon monoxide. So when you inhale, this explains, to understand, this is actually a very good way of explaining and understanding how carbon monoxide is really bad to inhale. And it's a very simple reason, saying that when you inhale carbon monoxide, the carbon monoxide forms a bond with the iron instead of the oxygen. And so instead of oxygen binding to the prosthetic group, it's carbon monoxide. And the reason why carbon monoxide poisoning occurs is because carbon monoxide forms an extremely strong bond with the iron. There's a higher affinity for the carbon monoxide with the heme group in comparison to oxygen and the heme group. So it forms a much stronger bond between the heme group and the carbon monoxide in comparison to in comparison to oxygen and the heme group. That's why carbon monoxide poisoning is such a big thing. And what happens is just because the bond is stronger. So it favors carbon monoxide over oxygen, which is not what we want. So carbon monoxide forms an extremely strong bond with the iron, and this is not going to break easily. And this means that the heme protein can no longer carry oxygen around the body, and this can starve the body of oxygen and cause death if enough of it is inhaled and for enough time. So this is a ligand exchange reaction, right? That's all. The oxygen. Sorry, I made a mistake. The oxygen associating to the heme group is not a substitution reaction. The oxygen will just bind to the heme group by association, but the actual ligand exchange reaction is when carbon monoxide is involved, because carbon monoxide will undergo a ligand substitution reaction with oxygen that's bonded to the ion, that's bonded to the heme prosthetic group. So if there's any oxygen that's associated or bonded to this group here, it'll actually undergo the ligand substitution and get rid of oxygen. So even if it's already bonded to it, it'll break the bond of oxygen to have the bond of carbon monoxide, because that bond is much stronger and much more favorable. So that's what occurs then when you inhale carbon monoxide. Okay, so this is just a couple of examples that you don't really need to know, so I'm just going to whiz through it quickly, but this is the end of the actual content of the video. So a key use of metal complexes is transporting oxygen in red blood cells. So this is great for us humans, as it allows us to transport oxygen around the body in the blood. Oxygen bonds to the iron to form a complex to allow itself to be carried. But the unhealthy part is that it helps us to explain carbon monoxide poisoning too. So carbon monoxide bonds more strongly to the iron than the oxygen, than the oxygen does. So carbon monoxide will always form a bond instead of the oxygen. So the red blood cells can no longer transport oxygen because they are all carrying carbon monoxide instead. And the body can't survive without oxygen, so carbon monoxide poisoning can be fatal. Hopefully that made sense. If this video didn't make any sense, this is the end of the video now. If anything didn't make sense, or if this was way too long, I could definitely shorten the next video. But I'm coming back into it, I'm coming back into it.